Good morning. I am delighted to have the opportunity of making this presentation. My name is Wenqi. I am a PhD studying in bioengineering at Polytechnic University of Milan. My research interests include deep learning, biomedical signal processing, and artificial intelligence in robotics. This paper focuses on designing a novel regression model based on deep neural network in robot tool dynamic identification for bilateral teleoperation. The presentation consists of 6 sections. I will introduce background about the teleoperation first, then the aim of this work will be given. The problem formulation is defined before we introduce the proposed methodology. Lastly, the comparison results are displayed and summarized in the last 2 sections. At the remote control of a slave manipulator by the human operator, the application of teleoperation has been adopted in numerous areas, such as robot-assisted minimal invasive surgery. In the surgical operation, the possibilities of some disadvantageous effects such as intraoperative injury and time-consuming will increase without haptic feedback. Hence, it is essential to provide haptic feedback of surgery interaction forces to the surgeon by using the bilateral teleoperation. For applying the interaction forces on the haptic manipulator, a 6-axis force sensor is mounted between the slave robot manipulator and the end effector surgical tool. Although the influences of the sensor size and the increment of the equipment cost can be ignored in this situation, some unexpected disturbances will be introduced due to the dynamics of the surgical tool. Previously, several approaches of dynamic identification using robot joint angles have been proposed based on the kinematic and dynamic models of the manipulator. In our previous work, several nonlinear regression approaches are adopted for modeling the tool dynamics using the tool orientation, such as co-fitting and artificial neural network-based methods. However, the approaches depending on kinematic model are challenging for industrial and biomedical robots, for which the joint Tokyo sensors are often unavailable. Also, all of them aimed to map 3-dimensional angular angles, which limited the accuracy because the tool dynamic includes the position moment. Meanwhile, the AN-based approaches have extremely poor robustness, which is easily affected by the problem of overfitting and underfitting. In this study, we proposed a novel deep convolutional neural network-based nonlinear regression model, which is a model-free approach. Secondly, the designed DCNN-based regression model aims to achieve fast computation and noise robustness. Lastly, the trained DCNN model is evaluated for online prediction. The regression problem can be described by the teleoperation scenario in robot-assisted surgery diagram. The force sensor is embedded between the robot end effector and the surgical instrument for providing force feedback. The force on the tool tip and the tool dynamic are measured at the same time, which is represented by the tool dynamics force function. In this work, we not only consider the static gravity force, but also the full tool dynamics as the input for accuracy enhancement. It has 15 dimensions, including position, angular angles, their corresponding velocity, and acceleration. Therefore, the aim of this work is to train a model F to predict the force based on the considered 15-dimensional input X. According to the limitations of our previous contributions, we developed a model-free based deep convolutional neural network structure for enhanced regression accuracy and fast computation, which is described in this diagram. It consists of 4 similar deep convolutional neural network models with a 2D convolutional layer, a rectified linear unit, and a batch normalization layer. The former one is to update the network independently, while the latter aims to solve the Venetian gradient problem for fast computation. The dropout layer is also adopted to avoid the large convolved feature vectors, causing the phenomenon of overfitting and time-consuming. This is the data stream of robot 2 dynamic identification for bilateral teleoperation by adopting the designed DCNN model. It can be seen the output has 3 dimensions of forces. There are 3 primary equipment I use in the real teleoperation system. The first one is the 7 degrees of freedom slave manipulator to operate the slave side. And the second one is the 6-6 force sensor to measure the contract force. And the third one is a cable-driven robot to serve as master manipulator for the teleoperation control. The regression error and online prediction time are the 2 important indexes to evaluate the performance of the proposed DCNN model. Hence, the root mean square error and online computational time are compared among those models. We add Gaussian noises with 4 types of signal-to-noise ratio into the raw signals to evaluate the ability of noise robustness among unidentified systems and 7 regression models, which are shown in comparison figures. From observing the results, both deep learning-based models are good at predicting the force of y and z axis. Notably, the proposed DCNN model gets the lowest average error for predicting fx. Furthermore, the standard deviation of DCNN approaches is lower than the other models, which means it is the most stable method for predicting noisy data. Similarly, by comparing the computational time in 3 kinds of batch length selection, namely 1, 5, and 10 samples, the proposed DCNN model got the lowest average in the sum of the computational time than the other methods, which is shown in Table 1. Our study aims to develop a model-free approach based on DCNN regression algorithms for achieving 2 dynamic identification for bilateral teleoperation, which features fast computation and noise robustness. For further work, more challenging problems will be considered in the bilateral teleoperation control system, such as the dead zone and time delays. The system tracking accuracy and stability might not be secured under these conditions, which remain the main preconditions for the success of the surgical procedure. That is the all content of my presentation, and thank you for your attention. If you have any questions, please contact us by email, and thank you.